As a mathematical formula, Bayes' theorem is a relatively straightforward extension of the probability rules that we've already learned. But over the course of this lesson, we'll see that it is actually one of the key tools in using probabilities to evaluate arguments. The focus of this first video, though, is just to give you some basic familiarity with the formula and some of the ways it's used. So in this lesson, we'll state two main formulations of Bayes' theorem, one towards the beginning and one at the end. You should be able to recognize what Bayes' theorem is used to calculate, a conditional probability. You should be able to derive Bayes' theorem in both its simple and expanded forms from the familiar rules of probability, and we'll cover that. And the video will also introduce the use of Bayes' theorem for testing the strength of evidence for a hypothesis. And that should give you a sense of the significance of this theorem. Previously, we covered that, in general, the probability of P given Q does not equal the probability of Q given P. So that's that inequality that's written there. Let's think about an example. The probability that Carl is a mammal, given that he is a cat, is 1. So that could be our P given Q. The probability that Carl is a cat, given that he's a mammal, is definitely not 1. So that doesn't equal Q given P. This shows that the order of P and Q in conditional probabilities matters. Since these two conditional probabilities are not necessarily equal, you might wonder then what the relationship between them is, if any. Well, there is one. We can calculate the probability of P given Q using the probability of Q given P, along with a few other probabilities. The formula that tells us how to do that, that's what Bayes' theorem is. So Bayes' theorem is a way of calculating the probability of some statement P given another statement Q. And in its simple form, Bayes' theorem is given by this equality here. The probability of P given Q equals the probability of Q given P times the probability of P divided by the probability of Q. Again, pay attention to the order of these statements. Our goal is to calculate the probability of P given Q. To do so, we need on the right-hand side there to know a different conditional probability, Q given P, as well as the probabilities of simple statements, P and Q. Where does this formula come from? Well, it can actually be derived in just 2 steps using the definition of conditional probability and the general conjunction rule, both of which we covered in lesson 9. So we start our derivation just by stating the definition of conditional probability. So that tells us that the probability of P given Q is equal to the probability of P and Q divided by the probability of Q. To get Bayes' theorem, we just have to substitute the equation that gives us the numerator, the probability of P and Q. The general conjunction rule tells us that that probability, the probability of P and Q on the top, is equal to the probability of Q given P times the probability of P. So we substitute the right-hand side of that equality into the numerator, and that gives us Bayes' rule up at the top there. As a formula, Bayes' theorem is really just an expanded rule for calculating a familiar kind of probability. We already did conditional probabilities, so the probability of P given Q should look relatively familiar. We just have a spelled out way of calculating it now. So remember that what the probability of P given Q is the proportion of the circumstances in which P is true if we start by taking Q to be true. So the conditional probability P given Q tells us assume Q is true and determine what proportion of the Q circumstances are also P circumstances. In terms of the Euler diagram, that is the ratio of the overlap of the circles to the whole Q circle. What Bayes' theorem does is it tells us we can calculate that ratio if we know three other values: the chance of P, the chance of Q, and the chance of Q given P. That's the proportion of circumstances where Q is true if we are operating under the assumption that P is true. Once you see that the theorem can be straightforwardly derived by combining formulas we've already introduced, it might not seem that novel or interesting. But its significance comes predominantly from one of the main ways it's used. Bayes' theorem is a useful tool for determining how well a piece of evidence supports a hypothesis. We'll use H to represent our hypothesis. So that could be, for example, that someone has a disease. And E represents our evidence. In our example, that could be symptoms of the disease, or it could be a positive test for the disease. Both of those provide some evidence for the hypothesis that the individual has the disease. Using H and E here, we can get an interpretation of Bayes' theorem. We substitute H in for P in our first version of the formula, and we substitute E in for Q. So every time you see a P, substitute in an H. Every time you see a Q, substitute in E, and we get this particular instance of the formula. On this way of interpreting Bayes' theorem, each probability has a special meaning. So we'll start first by talking about the probabilities we need to know. Those are the ones on the right-hand side of the equation. The probability of E on the bottom, that's just the chance of observing the evidence. So that would answer how likely are the symptoms to occur, or how likely is it that someone tests positive. The probability of H, the probability of our hypothesis, has a special name. It's called the prior probability. That value represents the initial chance that the hypothesis is true. Do we have some prior sense that the hypothesis is plausible? And how plausible is it? In our disease example, that would be, is the chance of having the disease high or is it rare? The last thing we need to know is the probability of E given H. That's called the likelihood. That name isn't very illuminating. The best way to think about this one is as the probability of the evidence being true given that the hypothesis is true. So what's the chance that if our hypothesis were true, it would predict that we would see that evidence? In our example, how likely would we be to have these symptoms if we had the disease, if it were true that we had the disease? What are we trying to determine? We're trying to determine the probability of H given E. That's on the left-hand side of the equation. This is called the posterior probability. Posterior in the sense of after we have the evidence. How likely is it that the hypothesis is true? So this value tells us how likely we should take our hypothesis to be on the condition that we have this piece of evidence E. If it's lower, we shouldn't be so confident that the hypothesis is true. If it's a higher number, we can be more confident that the hypothesis is true. So in the example we've been using, the probability of H given E would be the chance of having some disease given that you have certain symptoms or given that you have a positive test. We've been using this disease example to give you a flavor for the evidential interpretation of Bayes' theorem. And now let's look at how that interpretation works with some actual numbers. We're going to return to a familiar example from lesson 9.3. So in that example, we were told 3 out of 10,000 people have disease X. A test for disease X gives false positives 1% of the time and false negatives 0.5% of the time. In this case, as we've hinted in our discussion already, our evidence is T, that an individual tests positive for disease X. The hypothesis we're looking to evaluate is D. Does the individual have disease X or not? The hypothesis is that they do have disease X. That's what D is. That relationship should make some sense. Testing positive for disease is evidence that you have it. But how good is that evidence? How certain should you be that you have the rare disease X if you were to test positive? That's what we want to find out. That's the probability of D given T. So to get the value we're interested in, the probability of D given T, the chance that you have the disease given that you test positive, we first need to get our formula straight. So going into our evidential interpretation, we're substituting in T everywhere we saw E, that's our evidence, and we've got D everywhere we saw an H, that's our hypothesis. Again, remember that the order of the sentences D and T in the formula really matters. Once we've spelled out our formula, it tells us that in order to get the probability of D given T, we need to have the values, the probability of T given D, the probability of D, and the probability of T, in order to calculate our posterior probability. The probability of D is 0.0003, 3 in 10,000. That's the chance that your hypothesis is true, the chance of having the disease. That's pretty low. When we looked at this problem before, we calculated the probability of T testing positive, given that you have the disease. That's called the true positive in the case of disease testing, the chance of testing positive if you have it. And we discussed that we can get that value by subtracting the probability of a false negative from 1, the total possible probability. So that gives us the chance of a true positive as 0.995. And finally, we need to know the probability of T. Just how likely is it that we would test positive for the disease at all? This is what we calculated before using the law of total probability. So drawing the number from our previous look at this example, we had that the probability of T was 0.013, or about that. Plugging in those numbers that we just listed out, we get the chance that someone has the disease, given that they test positive, as only 0.023. That means that if 1,000 random people test positive, only 23 of them would actually have the disease. Why such a low chance, given that these people have tested positive for it? It seems like if you test positive, it should be pretty likely that you have it, especially since the test is accurate. Well, even though the test is pretty accurate, we have to account for the fact that the chance of the disease itself is very low. So the value of Bayes' theorem is that it allows you to take into account the prior chance of your hypothesis being true when you go to weigh your evidence. So what's the prior chance of someone having the disease? It's very low. Since the disease is so rare, testing positive isn't on its own very good evidence that someone has the disease. Here's something to think about. How do you think the chance of having COVID, given that you test positive, compares to this situation with disease X? I want to highlight one additional feature of our example. When we calculated the probability of having the disease given that you test positive, we relied on already having calculated the probability of testing positive. Remember, in 9.3, we used the law of total probability to get that value. Well, this actually leads us to our second common formulation of Bayes' theorem. So to get this expanded version, we use the law of total probability to give us a way to calculate the denominator in Bayes' theorem. So that's the probability of Q. The law of total probability told us we could get the probability of Q by adding together how likely Q was in two mutually exclusive and exhaustive possibilities, when P is true and when P is false. Right? So with P and with not P. Again, using the law of total probability, we substitute in for the probability of Q in the denominator to get our expanded version of Bayes' theorem on the bottom here. So what's on top hasn't changed. It's still the probability of Q given P times the probability of P. But we've expanded out what's on the bottom. We have a formula that gives us the probability of Q. Now we're adding together the probability of Q given P times the probability of P with the probability of Q given not P times the probability of not P. You should make sure that you're comfortable with both versions of the formula for Bayes' theorem. And one way of doing so might be to go back and look at this example that we've just covered, both here and when we looked at the law of total probability. Combining those two parts of this example gives us a full example of Bayes' theorem in its expanded form. With that, you should have some beginning familiarity with the formula for Bayes' theorem. And in later videos in this lesson, we'll cover how to use Bayes' theorem more, including as a way to evaluate inductive arguments.